In this video, we're going to count how many triangles are there in an n by n grid. So, for example, about what I mean, here's a 2 by 2 grid, consists of 4 dots. There are 4 triangles that you can make using the 4 dots in this grid. Here is one of the triangles, here's another one, and here's the last one. For another example, let's consider a 3 by 3 grid. So that is a grid that has 9 dots in it. Turns out there are 76 different triangles that you could draw using this grid. Just to show you a few, here's one, but I'm not saying they have to be right triangles, so here's one, and I'm not saying they have to be pretty like that one, and so here's one, so etc. So there's 76 different ones of these. So notice that the number of triangles grows very quickly with the size of the grid. What's the pattern? In other words, how does the number of triangles depend on n? So let's make some observations. The first thing, a triangle has 3 vertices, in other words, corners. The second thing, if the 3 vertices are collinear, in other words, on a line, so like that, then we should not count that as a triangle. So 1 and 2 suggest number 3. Well, the total number of triangles in an n by n grid, that ought to be, how many ways could you pick 3 of the n squared points to be your vertices of the triangle, right? There's n squared points in your n by n grid, but minus how many of those ways pick the 3 points all on the same line. So the 2 things that we need to count to answer our question about how many triangles there are, we need to count each of these 2 things. How many ways could you pick 3 out of the n squared vertices, minus how many ways could you pick 3 of them to be on the same line. So here's the tools that we need in order to do that. The first tool that we need is what's called the binomial coefficient. And I'm going to read this as n choose k, and you'll see why I'm saying the word choose shortly. What this represents, it's the number of ways to choose k things from n options, but there's no repetition, and the order of selection does not matter. Now the values of n choose k, they're typically displayed in a famous little thing called Pascal's triangle, and I'll show you a few lines of it right here and how you should read this. The first row, that stands for 0 choose 0, so 0 choose 0 is 1. The second row, 1 choose 0 is 1, 1 choose 1 is 1, etc. through all the rows here. And so those are the first few values of n choose k computed for different n's and k's as you go. And there's lots of cool little patterns in Pascal's triangle, and there are inductive ways to actually get a formula for what n choose k is. But what I'm going to show you is a more computational formula that uses what are called combinations. And this is something that you'd be able to find on a calculator or just punch in manually by hand. It is n factorial divided by n minus k quantity factorial, also divided by k factorial. But on any scientific calculator, you would have a button that is like subscript n, big C, subscript k, or vice versa with subscripts and superscripts. And in Desmos, if you click functions, scroll all the way to the bottom, you see NCR here. Sometimes R is used instead of k. So most scientific calculators have a button that gives you the binomial coefficient. All right, the next tool that we need is just a definition. We're going to say that a line segment in the grid is maximal if it's not part of a larger line segment. So here's what I mean by that. Here's my grid. These 2 line segments, they're both maximal because neither of those green lines are part of a larger line. On the other hand, this dotted red line is not maximal because it's part of that green line. So let's go. Let's get into our formula. Remember, what we're trying to do is we're trying to figure out the total number of triangles in an n by n grid. And what we said earlier is that should be how many ways could you pick 3 vertices from the n squared options minus how many ways could you pick 3 of those points to lie on the same line. Well, we've got a tool to count this nice green one. That's just n squared choose 3 minus more work. So how do we actually count this gold stuff? How many ways could we pick 3 points that are all on the same line? And what we're going to do is use the 3 by 3 and the 4 by 4 cases just to get an idea about the different ways that you could get 3 collinear vertices. And so here are the 3 by 3 and 4 by 4 cases, and let's dive into what's going on here. Now here are some ideas. If 3 points are collinear, then there's only one maximal line segment that they all live on. And so to give you an example, if you look at that 4 by 4 one, if I took those 3 collinear points, there's only one green line that they all lie on. So what we need to do is to count how many maximal line segments have at least 3 points. Another idea. After we do that, then we can count how many ways could we just choose 3 points from any of those line segments. So let's see what's going on. Here's the 3 by 3 case, and let's look at the number of lines that have 3 points on them. Well, you could have these 3 vertical lines, or you could have these 3 horizontal lines, or you could have this diagonal line or this diagonal lines. Those are all your options. So there's 3 plus 3 plus 2, which is 8 of them. So there are 8 lines that have exactly 3 points on them. And now, for any of these lines, there are 3 choose 3 ways to pick 3 points from that line. In other words, there's only one way to pick all 3 points from any one of these lines. Thus, for the 3 by 3 case, the number of ways to pick 3 collinear vertices would be 8 times 1. So 8 times 3 choose 3, and that gives me 8. Now, moving on to the 4 by 4 case. Remember, we're just thinking about how to count the gold right now. So here's the 4 by 4 grid, and let's start again. Let's figure out the number of maximal line segments that have the maximal number of points, 4. So n equals 4 here. And again, I get these 4 vertical lines, these 4 horizontal lines, plus these 2 diagonal lines. So in this case, it's 4 plus 4 plus 2, which is 10 lines. So 10 lines have 4 points on them. Now, there are 4 choose 3 ways, in other words, 4 ways to choose 3 points from such a line. All right, back to the 4 by 4 grid. Now let's think about maximal line segments that have 3 points on them. Well, there are 4 of them right here. And now for any of those 4 lines, there are 3 choose 3, which is one way to pick all 3 points on that line. So thus, for the 4 by 4 case, what we've got so far is the number of ways to pick 3 collinear vertices should be equal to 10 times 4 choose 3 plus 4 times 1, which is 3 choose 3. And that's a total of 44 ways to pick 3 collinear vertices. Now what we want to do is think about what's going on in general. So I've just drawn a slightly bigger grid here, and I just want to try to think of some patterns that maybe I noticed above. And I'm going to write the patterns down, and rather than scroll back up, I encourage you to rewatch maybe the parts for n equals 3 and n equals 4 to see where I'm getting these general formulas. There are going to be 2n plus 2 maximal line segments that have n vertices on them. There are n horizontal ones and n vertical line segments, so that's 2n, plus you get the 2 main diagonals. Now, there are going to be 4 maximal line segments that have n minus 1 vertices, so 1 less than the most number of points a line segment could have. And so here they are here. Continuing this way, there are 4 maximal line segments that have n minus 2 vertices, and here they are here. And this pattern just continues. And there are going to be 4 maximal line segments that have 3 vertices, and here they are here. So, to put it together, the n by n case suggests that the number of ways to pick 3 collinear vertices should be 2n plus 2 times how many ways you could pick 3 of those n points on that line, so times n choose 3, plus 4 times how many ways could you pick 3 points on that line that has n minus 1 options, plus 4 times how many ways you could pick 3 points from n minus 2 options, and you keep doing that all the way till you get down to plus 4 lines where you pick 3 points from the 3 options. Now what we're going to do is some algebra. So I'm going to keep 2n plus 2 times n choose 3. So I could factor a 4 out of all those things on the right. And then what we're left with inside is this. And I've colored that pink because there are, again, special binomial formulas or little properties that people know from Pascal's triangle, and I'm just going to present one to you here. A binomial identity says that that quantity is actually equal to n plus 1 choose 4 minus n choose 3. And again, that's kind of magic, but I encourage you to read more about Pascal's triangle and binomial formulas and some other binomial identities, and you'll probably stumble across one that you could use to derive this one. Now what we're going to do is we're just going to substitute that expression inside of where our brackets are right here. Now what we're going to do is just a little bit more algebra. We're going to distribute that 4 through, and notice you've got some things called n choose 3 already. In the front, I've got 2n plus 2 of them, and now I'm going to subtract 4 of them when I distribute that 4. So think about 2n plus 2 minus 4. That leaves you with 2n minus 2 of your n choose 3 things, plus 4 times n plus 1 choose 4. And that is going to be our general formula for how many ways that 3 of the vertices could be collinear in your n by n grid. So finally, put it all together, the total number of triangles in an n by n grid should be equal to n squared choose 3 minus 2n minus 2 times n choose 3 plus 4 times n plus 1 choose 4. Now I wanted to demonstrate to you that this formula works and it recovers a lot of the values that you might find on the internet if you look up specific values, like how many triangles are on a 3x3 grid, a 4x4 grid, or a 5x5 grid. And so we see that it matches some of these values that the internet suggests are true.